All right, so welcome everyone. Welcome aboard COP352 with service to Vegas, right? So fasten your seatbelts and hold on to your wallets because the cloud journey can get pretty damn expensive, but that's what we're trying to help you with and provide some best practices around that, right? And well, you're also going to get some refreshments served in the form of lots of data points, no shortage of that. And for those of you that have just come off long flights or flying international, apologies for continuing that one. But it only gets better from here. So I'm Ravi. I'm part of the Xeon software team at Intel, and I'm joined by Ambud.
Yeah, hi, my name is Ambud. I'm Trust.
All right. So let's jump right in. Okay. So we'll start with a few cloud computing trends. And a lot of this will be familiar to you, and the source of all that is right at the bottom if you want to refer to it. But let's have a quick show of hands. How many of you are concerned about cloud spend? Most of you, and that's pretty self-explanatory, that's been a very clear focus, especially for the last couple of years. And that's something that we want to focus on. And cloud, especially where spend is concerned, software efficiency can matter a lot. If you can drive efficiencies by reducing your instance size, reducing the number of instances, that's something that immediately will show up in your next month's bill or what have you. That's something that's compelling. That is not possible on-premises environments. And it goes beyond compute optimization. If you're deploying something like a compression optimization, you save on network, you save on storage. For those of you that have seen your AWS bill, that EC2 other category can be pretty large, sometimes larger than your instance cost itself. The other thing that you look at is how your software architecture is actually defined. In many cases, we see examples where software architecture decisions are based on the cloud pricing, not on what the instance is actually capable of. That might resonate with some of you, right? As an example, I know that there's some people that have made a choice of where they replicate data because of the cross-region cost of transferring traffic, right? And those are decisions not based on instance capability, but based on cloud pricing, right? And the second thing that we're looking at is security. And security is pretty broad, right? But here we're talking specifically about encryption, and that's quite important. And in encryption, we can further break it down into three things. Encrypted connections are pervasive, like that data point shows. You're going to see end-to-end encryption for any kind of connectivity, but you're also increasingly seeing encryption of data at rest. So you're reading and writing encrypted data. And now what's picking up is encryption of data in use as well, right? And that is something that is a clear trend. It adds potentially some overheads, but it is soon becoming a necessity. Right? And last, but certainly not least, right? The cost of development can be higher than the cost of infrastructure. There's an aspect of scale to all of this. So obviously, it matters what scale you're operating at, how much is your infrastructure spend versus your development cost. And more than anything else, what we want to look at is how you can actually reduce infra cost, right, and make developer time to market faster, right? That's generally the intent. And one of the points here is, if your code does not need to scale linearly, it's not a zero-end operation effectively. When you have to scale out, your cost is not going to be proportional, right? And that's a big deal. Right? And if you think about the hardware trends, and let's be honest, nobody running in the cloud wants to or really deal with hardware. That's the whole point of the cloud, right? But being aware of what the capabilities are and how to take advantage of it without needing to care about it is something important, because otherwise you leave performance on the table. And this might seem like a little bit of a conundrum. What I mean is, if you want to be moving fast and you don't want to care about what the underlying hardware is, how do you still manage to make the most out of performance, right? And so let's go into the next one, kind of looking at what that might imply, right? Well, the diagram on the right, I don't even have to talk to it. There's a version of this on every possible website out there. All of you are familiar with it. It's a fairly standard thing. What the red line is representing is essentially or how the AWS calls it, the shared responsibility model. So if you're running a Lambda function, for example, all you care about is that function and nothing else. If you're running a Snowball Edge or an Outpost on premises, you care about many more layers of that stack. But what this is really talking about is the fact that the top 2 layers are generally the ones that move very fast. That is what is really focus on, well, that's what most developers focus on from a time to market point of view. The rest of the layers, not so fast, right? And there are common primitives, as this list of examples shows, which consume a significant amount of CPU time. And most of those are not really top of mind, right? So how do you deal with this? What the title is showing is, or saying is really, performance requires specialization. But to move faster, you need standardization. And are they really mutually exclusive? And as that operator in the title shows, it's actually an and, it's not an or. And the reason I say that is, if you have the lowest common denominator, you have a problem. What I mean is, if you look at, for example, your glibc. libc is the most common library used by every single application that you're running on Linux. Go check the version of glibc that's running in your distribution and check when it was released. You are probably running software that was designed for hardware that is now obsolete. And it's not even a exaggeration, it's probably the reality. Right? So there's a lot of opportunities with primitives, and what I'm calling as common primitives is that list of examples. Right? And that's the takeaway in a sense. Even if it's a small percentage consumption, depending on your scale, that can be a huge performance gain and a cost reduction, depending on the amount of optimization you're able to do over there. Right? So that's the takeaway of that slide. So let's take a moment to talk about microservices. And again, I don't need to explain the diagram at all. It's very familiar. The vast majority of every single cloud-hosted website instance is probably designed that way. Right? So Ben over there checking his feed is probably generating a few thousand API calls, and that in turn is going to be generating trillions of instructions. And that is how we look at things when we do deep profiling. So being able to deal with a set of requests that are going through that entire layer, through a load balancer to the compute layer, through all the microservices, to the database and the backend, and then back again, is generating literally trillions of instructions per minute. And what we do is look at opportunities, both opportunities to identify bottlenecks and opportunities for optimization. And the way we look at it effectively, in a way, our view of the world, the Intel view of the world, is there is a theoretical maximum instructions per cycle IPC that you can get. And the profiling will show you what your actual IPC is. And the intent and the goal of optimization, the goal is simple. You want to maximize that IPC as much as possible, get it as close to that theoretical max as possible. Right? The actual theoretical max you won't hit, but that is the way of very simply stating what the general goal is. Right? And I'm going to hand you over now to Pinterest, and Ambud will talk through a real-world set of examples that we have collaborated with them on this performance optimization journey. So over to you.
Thanks, Ravi. So a quick intro of Pinterest. Pinterest is a visual discovery platform and inspiration platform for shopping and discovering best ideas in the world. It's basically like a digital bazaar. And just like Enid, I use Pinterest frequently for my home improvement and woodworking hobbies. So let's see what makes Pinterest work. We have over 300 plus services with a shared service stack using open source technologies that run over tens of thousands of EC2 instances with exabyte scale data on Amazon S3. And what are our challenges? Well, there are two key challenges that we care about. First is scaling services on demand, which means that being able to service requests as they increase when we have new features released or the user role increases. And we want to look at optimizing our infrastructure to be able to save cost. What this really translates into is we have to solve efficiency problems and optimization problems deeply within our infrastructure. But these can be very challenging at our scale because validation is pretty complicated at our scale. So let's see what we developed collaboratively with Intel. What we have is an optimization process which allows us to converge via an iterative approach to get to a point where we have better and better code, and efficiency running in our platform. Our process is ROI driven, which means that once we see there is little to no return on investment, we stop optimizing. And how we determine that is by understanding what's the effort to optimize something and what's the amount of dollars or cost or if performance improved based on that. And this process helps us make sure that there is discipline around this via a root cause analysis approach. So try to figure out what's wrong, then figure out why that's the case. And we kind of go through a 5 whys analysis trying to figure out to get to the bottom of why we are seeing performance issues or cost efficiency problems. And then this optimization process itself is a 4-step loop. And what that looks like is this. We go through hypothesizing, trying to figure out what could be potentially happening here, what are the potential challenges. We try to verify that by using tools like profilers and partnering with Intel on getting hardware level profiling with PMUs. And then we try to figure out how could we implement that? What would that be, a config change, code change, or a platform level change? And platform change also, by the way, means that we might be thinking about hardware upgrades in that case. And then once we have gone through that process, we look at validation. Is our original hypothesis correct? Did the data show that it's doing exactly what we thought it would? And were there any degradations in the service? Were there any unintended consequences? And this is looking at service KPIs like request throughput, latency, or success rate. And if all of that checks out, then we make a decision between whether to roll forward or roll back. And rollout can be very service specific, because if you're looking at a database which is distributed and replicated, even changing a single node can have the entire cluster-wide impact. So you got to be very careful. Now let's talk about 3 such use cases at Pinterest which demonstrate leveraging these optimizations in this approach for both hardware and software level optimizations. The first one is our data uploader or S3 uploader service, which is called Merced. It removes data from our PubSub environment into our S3 data lake environment by recompressing it and sorting it. So we do time sorting of it based on event time, and when the data is ingested, it's ordered by ingestion time. So we want to resort the data, try to figure out when the event actually happened, because that's what drives our business metrics. And given the nature of this service, right, the objective here is that can we reduce costs without lowering our throughput? Can we not change the availability of the service here and destabilize the service any which way, right? Simplest thing is like, hey, let's cut the amount of hardware it's running, right? And maybe we can save some money. But the point here is that might destabilize service or have other unintended consequences. So our hypothesis here is, again, compression seems to be the key point here, and compression and decompression is what this service is doing in terms of tasks. And we primarily use gzip because of the superior price, the superior compression ratio that we see with gzip on our data set. We confirmed this hypothesis by running profiler. And as you can see, there is an output of perftop here, and you can see libz being very popular in the perftop output. So once we verified this, our hypothesis was, well, if we could optimize the compression, as Ravi mentioned, can we optimize compression here? Could we reduce the cost or increase the throughput of the service? So what we ended up doing, we asked ourselves, are there efficient compression libraries that we could use? ZSTD is very popular because of its performance. But the challenge with ZSTD is, in the case of Java, ZSTD calls are invoked via JNI. Again, there are native implementations as well for Java, but the popular one is the JNI-based implementation. So for small batches of data, the overhead of JNI calls is very high, to the point where it actually negates any optimizations or performance improvements you'd get out of it. And this, for the small cases, as I mentioned, doesn't save CPU and instead causes degradations of performance, right? So the other part is that because if we wanted to do reduction of batch sizes to get ZSTD rollout, increasing of batch sizes to get ZSTD rollout so as to get more and more data and reduce the number of JNI invocations we were seeing, we would have to potentially impact the trade-off, the latency of it, because not every pipeline will generate the data at the same rate. So if you want to accumulate more data, you have to increase the latency so as to accumulate to be able to get bigger batches. So we wanted to solve the gzip compression problem regardless. And what ended up happening was we were looking at what are the gzip optimization options there, right? Specifically, we're looking for something that was vectorized and had SIMD capabilities because we know that those instructions exist on the hardware, and we could just leverage that. That's hardware that's sitting there. We are not able to leverage it today, but if we could start leveraging it, we'd get more performance. So upon researching this, we found 3 options. We found zlibng, we found the Intel IPP library, as well as the zlib Cloudflare library. There's also zlib Chromium, by the way. So we tested these 3 libraries, and what we found was zlibng provided the best price performance on that. And to the point where you see the chart, it reduced the CPU utilization by up to 50% in certain cases. You see 40 to 25% drop, 40% down to 25% drop in terms of CPU usage. And what this does is after combining this optimization with hardware upgrade from going from C5D to C6ID, we see a net reduction of 50% for CPU. And that translates to 30 to 40% improvement in cost efficiency per cluster. So we were able to not only reduce cost in some cases, but we were able to run more workload through that cluster. And this is done all without destabilizing the service or impacting throughput. What was also interesting is actually our throughput went up with this. So not only are we saving money in this case, we're also getting more throughput. So if you may be familiar with Kafka catch-up reads, when the consumer resets and it has to read a little bit of data, go back and reread some of the data, that went faster. So our average peak utilization of CPU for the cluster came down, and therefore we could run a smaller cluster and not have as much degradation when let's say an instance failed and there was a catch-up reads happening. Let's talk about another popular use case in the industry, which is Apache Kafka. It's a commonly used pub subsystem. Many of you may be using it. And at Pinterest, it's used to power over 50% of the pub sub traffic. The objective in this case was, again, to look at reduction of cost without impacting the latency. And what's interesting at Pinterest is our Kafka clusters are CPU or disk bound. And the reason is because we had done several optimizations ahead of time in the past. And therefore, what that meant is that if we reduce the amount of CPU utilization, we could therefore get the opportunity to reduce the size of the cluster or do right sizing of the instances that we were using. And what we found was that in the past, we had avoided profiling the cluster because profiling overhead could be high in production. We were not able to simulate this problem in non-prod. So if we plugged in the profiler, it would degrade the latency of production, destabilizing the cluster. Pretty bad idea, given that it's powering some very critical things for the company. So what we ended up doing instead was asking Intel, hey, can you try to benchmark this or simulate this workload and see what you see in terms of bottlenecks. And what they found was, well, it's actually compression that's causing it. We're like, wait, what? That doesn't make sense. The reason it was compression was like, the reason it didn't make sense to us was because, well, we use producer-side compression, right? So the producer is actually the compression, not the brokers, right? So why would the broker be looking at compression? And the answer was because it was looking at the metadata. So it's actually looking at request payload metadata. And especially if you're running low latency pipeline, there's a lot of requests being generated. So what ended up happening was, what we had originally assumed was it's just the request rates that we're seeing. It was a combination of both, right? It's the number of requests that are being generated, and what it's doing in that request is decompressing data. So combine them together, that was the primary reason what was going on here. And as you can see in the perf top screenshot there, you can see inflate running, and that's a clear indicator of what's going on. Obviously, we did symbol translation with Intel with low overhead profiling to see what else was going on. And what we saw in that case, it was not just these two things that were happening, which is high request rate and compression. It was also SSL and gzip that were causing contributions to higher CPU utilization. And Intel had already shared with us the amount of contributions they have done to JDK 11 and 17. So we were like, hey, they've already optimized this. We can just use the acceleration for SSL out of the box and save CPU on that case. So what we ended up doing was actually a combination of these optimizations. Again, using our iterative optimization process, we swapped gzip to zstd where it was feasible, wherever the latency budgets permitted it. We did zlib from zlib to zlibng and libzip to zlibng swaps wherever we could, and for the remainder of the use cases. And again, also upgraded to JDK 17 to get the SSL performance improvements. Lastly, we also found some of our finicky GC settings were not right because they were overly indexing generational heap in a certain way, and we wanted to fix that. So all in all, when we did the rollout, as you can see, if you just did the ZSTD rollout with a request rate reduction, it would kind of near about 40 to 50% reduction in CPU, because what we did was we first reduced the size of the cluster, then when we roll out the optimization, and we can see the CPU chart gracefully comes back to where it was. But when we apply all of these optimizations, you can see that one node that we have shown, like that's the entire cluster, and we see that one node kind of chugging along at the bottom. That's after all the optimizations have been implemented. Net, in certain cases, over 50% reduction in CPU, and no degradation to latency or throughput. Actually, in fact, it would improve because you're using accelerations in this case. And then what we did was a phased rollout in production environment, 25 to 50% reduction in cost per cluster. So we were able to address this. And by the way, we did all of this optimization on I4I. This was also a migration from I3 to I4I to get these performance changes implemented. Let's talk about one more use case, which is key value store, which a lot of you may be running in your node environments. Ours is called Rockstore. It's no guesses that it's built on RocksDB. It's a distributed key value store. And again, objective here is don't compromise the SLO, try to see if you can get more performance out of it or save cost. And the hypothesis is, well, why is the CPU causing issues in this case, right? Let's find out. When we did the flame graph analysis, the perf analysis, we see, well, it's actually something called time series histogram happening. It was like, why is our key value store doing time series histograms? Turns out it's just monitoring the key value store itself. And that's basically eating up majority of the CPUs. Like, that doesn't make any sense. It should be an auxiliary service. It should not be the core thing that's compromising the CPU on the instances. So what we ended up doing was trying to work with the team and actually fixing what the problem was. And what was the problem? The problem was that we didn't have a GC process for when shards would rebalance in the cluster. So the metrics would not get evicted out, because usually those are singletons, and you're creating a centralized observability store within the machine. So you're trying to get gauges going, and those gauges would never get deleted. So you just keep adding gauges after gauges to a point where it's just the primary thing that the machine is doing. What's interesting is the moment you restart the process, the CPU just drops. It's like, well, with that doesn't make sense. It's like, okay, well, the workload didn't change. We didn't do a shard rebalance. What was going on? So once we fix that bug, as you can see, there is an improvement in CPU, and dramatic improvement in CPU. So this combined with the I3 to I4I optimization, once again, we see a reduction of 20 to 25% based on the instance swap alone, and 10% on an absolute basis in terms of CPU utilization for a given cluster. Just cut out from the CPU. All in all, this is something that we are currently migrating and actively working on rolling out. So far, we have seen 15 to 20% improvement in terms of net price performance that we're getting. So overall, it's a happy path for us that we want to pursue forward. All right, to sum it up, a couple takeaways. Well, we see clear price performance advantages using the latest Intel instances, specifically the ones that are focused on I/O. As we saw with the workloads like Merced, Kafka, key value store, and we also see this in heavily threaded applications. For example, our routing layers, which are hundreds of threads at a time to be able to service requests in low latency manner. We also saw firsthand what SIMD and vectorization could do in terms of efficiency gains. And again, the point is, the more we can lift and shift things into the SIMD space, which is by all means challenging, but Intel's been doing a great job building these libraries for us that we can just use it with acceleration out of the box. And then gen over gen upgrades are great way to get savings out of the box, right? It's something like, hey, I don't want to do optimizations in terms of code changes or config changes. Can I get savings out of the box? And the answer is yes. If you just try your gen over gen updates, plug in the new machines, see how they behave in your environment, you might be able to get better price performance. We also saw multiple times that optimizations have to be done in tandem, right? So we have to have a methodical process to be able to see how to roll out an optimization. Sometimes you may have to optimize CPU and memory together, or memory and I/O together. Basically, let's say if you're using page cache versus local disk. So you have to balance those things out, and net target optimization that you're trying to achieve will be a combination of these optimization. And last, not everything goes as planned, right? So one thing that we didn't share about or said is that, well, the way we did the zlibng rollout was like, hey, let's install it on the OS itself. Well, something else uses it, which is Docker, and there was a bug which was causing unpig-z to basically lock up and break our Docker deployment environment on the given machine. So bad idea. We had to change our strategy and package the library with the application itself. So this is something that, these are things that, like, not everything would go as planned. As I previously mentioned, that you may have to roll out or roll back changes and kind of iterate on your approach. So with that said, like, that's what we have from Pinterest on optimizing in the cloud. And we're back to Ravi.
Thank you very much. That was pretty impressive. Okay, so I'm going to jump into some benchmark numbers. So we saw what was achieved going from C5 to C6 ID, and we've been working with Amrut and many other customers on going to the latest gen instances. Anyone here that has already tried the M7i or the C7i or the R7i instances? Not very many, and not surprising, they're very recently released. So these are benchmark numbers that you see where you have, well, components that are fairly common in most deployments, especially microservices deployments. Right? And of course, these are benchmarks, right? And as our esteemed fellow at Intel, Brendan Gregg, has said, all benchmarks are probably wrong. Some are useful. These are sort of useful. What I mean by that is you don't have to go by the explicit numbers there. Obviously, these are tuned and these are benchmarks, which is why that bullet point says you should get around 20% higher, even though the benchmarks here show that with tuning you can get even more of a performance improvement going from the 6th gen Intel-based instances to the 7th gen one. Right? And also, you have clear scaling that you can do across a bunch of these. One of the other things that is new, that is not really well known or common, is that you now, for the first time, have performance counters, the core performance counters, available in every instance size. AWS was actually the pioneer in introducing these performance counters. It was only available in the single socket size or the full instance size until now. With this latest generation, you have the core performance counters available in every instance size. And that makes all of the profiling and debugging that Ambud was talking about to identify bottlenecks much more easy. Right? So that's something that we're really excited about. And the overhead when you do sampling and profiling with these performance counters, because they're hardware performance counters, is much lower than doing it with software alone. Okay, so can't not talk about Gen AI and LLMs, right? It is the topic of the year. But caveat, of course, is when you have a purpose-built function-specific accelerator, a general-purpose CPU can't easily compete. However, this generation of Intel instances comes with AMX, right? And so as an example of what it's capable of, at the lowest level, an AVX 512 unit can do 85 operations per core per cycle, and AMX can do 2048 operations, so 2 TOPS per core per cycle, right? So it's a substantial jump. And so it is fairly capable. It also supports bfloat 16 and int8. And in general, for large language models and use cases like chatbots, the primary metric really is the second token latency, right? And that's what we look at. And what we have is data that shows that you can hit the sub 50 millisecond and sub 100 millisecond numbers. And so the first one here, and this is with the int8 data type. With bfloat 16, the latency numbers are slightly higher, but still within the range. And these are on a 16XL M7i. You can get relatively close to this even on an 8XL, although that data isn't in here, but we'll be publishing that very shortly. Right? And what this is showing you here, right? This is with a Llama 2 7 billion parameter model, right? And you can see that you're hitting the second token latency that is well within the bound. And that's the main thing, the 50 and 100. And if you look at a larger one, so this is the sub 20 billion, so this is Llama 2 13 billion model, right? And on the same instance size, right, you can see that you can get second token latency below 100 milliseconds, right? And these are, of course, again, benchmarks, but these are standardized benchmarks that we're using here. But the other thing is also the tools and the ecosystem enabling that we've been doing, right? And this is relatively recent. Hugging Face, which is like GitHub for LLMs in a way, right? Hugging Face has a leaderboard on open source LLMs, and Intel optimized neural chat is actually #1 right now in the sub 7 billion LLM leaderboard, right? And we also have optimizations that plug into PyTorch that work with TensorFlow, and there's also tools like Neural Compressor that lets you do int8 or bfloat 16 if you've got a FP32 trained GPU model. You can just chop off the bits or do fine-tuning, right? So this is something that's very compelling. We've got a lot of customers that are using this alongside other workloads that they're running anyway, especially in a scenario where you may not be able to get GPUs or you don't want to have to pay that premium. Okay, so before I jump into this one, a quick question. How many people here have used metal instances on AWS? There's a couple of folks. So generally, the perception is that metal instances are only for enterprise legacy software where you need node-locked licenses, and why else would you use it? It takes much longer to spin up. You can't easily add it to an auto-scaling group, and so on. But we work with numerous customers, especially ones that operate at large scale, that prefer to do their own bin packing. So you're not limited by the vCPU memory ratio of general instances. You can define that yourself when you're running on a metal. You also have full access to all of the core counters and uncore performance counters. You can control the uncore frequency. All of these are useful and important, especially when you have profiled your application and you know what the performance is, what the dependencies are. But on this generation, the latest generation of metal instances, there's a few unique things. The first thing is there's a single socket sized metal instance. That's exciting because you don't need to worry about NUMA overheads at all. You just pick the single socket instance, there's no NUMA. Right? And the second, even more important from that point of view, is you have accelerators. Right? And there are 4 accelerators, but I'll go over one of them. But there are 4 accelerators. One is a data movement accelerator, DSA. The other is the analytics accelerator, IAA, QAT, which is what is being showcased here, which we're working with Pinterest on. Right, for both encryption and compression acceleration, and there's also DLB, which is for hardware-supported queue management. So what this data is showing you is 2 data points, right, on the chart. The dark blue is the 1.0, the baseline, and these are all on M7i. And the light blue is the performance when you use the crypto instructions. That is available in every instance of both M6i and M7i. Right? And the light yellow and the orange are with QAT, with a single QAT device and 2 QAT devices. On a single socket metal instance, you get 4 QAT devices. On a dual socket, you'll get 8. But what this is showing you is a 2x to 3x or 3.5x improvement in encryption throughput. And I was talking about the trends and how important encryption is. The throughput increase is also matched by a reduction in the CPU cycles that you need to use to achieve this, because you're offloading it. Right? Just like I mentioned during the LLM slide, a purpose-built function-specific accelerator will beat a general-purpose CPU. This is built for encryption and compression acceleration. And Ambud went over some of the compression optimizations that have helped them and the extent to which they've been useful, and we expect that to be supercharged with an accelerator that can do it. This data kind of speaks for itself. It's a micro benchmark effectively, but this is staggering, right? You can go up to 23x higher throughput on compression, and you can use potentially 96% fewer cores to achieve that. On an end-to-end workload, obviously it depends on how much time your application spends on compression, and that will differentiate what the impact of all of this is. Right? And last but certainly not least, these are not accelerator examples. These are again with ISAs, with SIMD and vectorization, right? And this is from the community. So data stacks, Unum Cloud, even Elastic for that matter, have all implemented faster vector search, which uses AVX and AVX 512, right? And the extent of improvement that they're seeing is quite staggering. We've started working with all of them to see how much more we can push this and how much further, right? And it isn't limited to specific things like this. The other chart at the bottom is actually a very simple common primitive again, where you can do encoding and decoding. And these are part of JDK, because Intel works with the JDK community and has been for a long period of time. These are in JDK 17, so these are measurements comparing the R6i to the R7iz, right? And so a staggering improvement in performance from just encode decode, and that's just one of the examples of the primitives that are there. Right? Okay, so let's switch to something else that is probably not very well known. Right? So Intel works with AWS quite extensively, and beyond just having Intel-based AWS instances, we have extensive software collaboration, and that's one of our probably best kept secrets for whatever reason. But this is something that we wanted to highlight. So I'll give a couple of examples, right? And all of those optimizations that we talked about, many of them are relevant to AWS services that a lot of you probably consume. Right? So for example, how many of you use the Elastic Load Balancer or the API Gateway or the Web Application Firewall? It's pretty pervasive, right? And well, all of them use the AWS foundational libraries, which are called the AWS Common Runtime Library, the CRT, right? And we've been contributing to CRT now over the last year or so, right? In fact, it was the last year's reInvent that we made the connection with the team, the cryptography team at AWS, and we started doing these. And those optimizations that we talked about are now part of these. So if you're running on ELB, if you're running on any of those applications that use these libraries, you're actually benefiting from them. And if you have services where you have the option to choose the instance type, then when you run on the latest instances, this will also get incorporated, right? And the second chart on the bottom, the first two charts on the top, they're showing you the encryption optimization with common encryption algorithms. AES GCM is the most common for encrypted connections, XTS for reading and writing encrypted data. The second chart on the bottom, I think there's a little segue first I need to do. So Andy Warfield, who's the VP and Distinguished Engineer at AWS, gave a talk earlier this year at FAST 23 conference, where he mentioned one data point, which is that S3 does 4 billion checksum operations per second. It's probably higher by now, right? That's a staggering number, right? And S3 uses this AWS checksums library to do that. Right? And we've been working with them to implement this optimization. This is not fully merged, but it's been accepted. So this one is giving them more than 3x improvement in throughput. And that is at the scale that S3 operates is absolutely massive. Right? So those are the kinds of optimizations that we do with AWS as well. And the other example I have is on a service. Right? And this is OpenSearch, which is a fork of Elasticsearch, and there's a managed service that AWS has on this, and we've been contributing to their open source fork of this. So we have extensive contributions planned and in the pipeline for OpenSearch as well. There was a joint Intel and AWS presentation at this year's OpenSearchCon in September, which is in the public domain from my team. And these best practices on tuning have now been documented in that link over there, so anyone can benefit from it. The latest instances are not yet available with OpenSearch. We expect that soon, but obviously OpenSearch is an open source project, so you can deploy it on the latest EC2 instances anytime. Okay, oh, fancy transition, okay. So one of the most common questions that I get asked at reInvent, this is just my second reInvent, so I guess the last time, was what is Intel doing at reInvent, right? What do you guys do here? And the point is that I think the extent of software contributions that we do is not very well understood, or not very well known, rather, right? And all of this is completely in the open source domain. Every single one of the optimizations that we spoke about, that I was sharing and that Ambud was talking about as well, they're all in the open source public domain. We generally follow an open source first policy, right? And it's across the stack, as you can see over here, right? And that is something that we plan to continue. And so what that really means is that for a lot of these kind of optimizations, if any of you want to take advantage of them, you don't necessarily have to work with Intel and have to do a deep dive into collaboration. You have the tools for profiling, the tools to identify the libraries that would be best suited, and to implement them all effectively in the public domain. Sometimes you need to pick the latest version of something, and in other cases you might have to pick the correct configurations, but you have those optimizations that are out there, and that's something that we continue to do. Okay, so this is more like a call to action, right? We shared a few examples and some data points, as I said, about the kind of performance optimizations that are possible. Obviously, I couldn't put the numbers in terms of how much performance optimization each of these can do, but these are examples. In general, AVX or AVX 512 or vectorization in general is assumed to be an HPC thing, or at the most maybe for certain things like media encoding, but it goes way beyond that. As this list shows, and again, this is not an exhaustive list. This is a set of examples, right, of where you can apply it. Right? It's pretty massive. And if you profile your application and you know how much time your application is spending on these different things, it can add up to a substantial amount. Right? And that's the main point there. And even if you do not want to deal with needing to identify the right library and so on, you have Intel Granulate as a solution, which is effectively a black box optimization method in a way. And what I mean by that is you don't have to worry about how the optimization is applied and what to debug. They will do automated profiling and do the optimization underneath. So that's an option. And we also have an optimization hub. That's the link and the QR code on the right, where you have ongoing updated list of these optimizations that are relevant for different instance generation sizes and types. Right? And obviously, we'll be working with AWS to make sure that all of these come into the next generation instances. And there's more ISAs and improvements that will come along the line as well. Okay, and that's all we had. Do you have any questions for us? I have a question. So when I was talking about the cloud spend, one of the things that I was going to ask is how many people got invites to go to cloud cost management company booths or other such events? Not too many. Interesting. That's almost like effectively like a trend or indicator of how much attention is potentially being paid to it. Right? That's one way to think about it. Okay, if there's no other questions, we can end. We'll be available after the talk if there are any other questions that you have for us that you think of later. Thank you very much.
Okay.